Yo. Meat and potatoes time.
Ooh, this one's the big one.
Redox half reactions. So we have to write oxidation and reduction half reactions. And in order to do that, whenever you're presented with a whole reaction, first thing you got to do is figure out what metal is involved in being replaced. Because these are all single replacement reactions, really, that we're going to show.
So there's the first piece. It is a single replacement reaction. When you see a double replacement reaction, that doesn't work.
Redox.
And then, we just got to basically figure out now.
Right. And so in this case, you can see that calcium and magnesium are going to swap in a single replacement, which means that we have to track the changes in the oxidation states for all the elements involved.
Right. And this basically proves we find the oxidation and we prove that there's a reduction when there's both. Now we know we're all situated, right?
So magnesium is becoming, well, let's see, he's got clicks.
Yeah, I got clicks. Well, so just looking at that MgBr2, I know Br is a -1 and there's two of them. So, and Mg's got to be then a
+2. And it is, in fact, the only option for magnesium.
Which is sweet. And then we learned whenever there's an element all by itself, it's automatically
oxidation state 0.
Bam.
So magnesium went from oxidation state +2, being a +2 cation, to being a pure element.
Yes.
And then the other thing happened too. Calcium was a pure element by itself.
0.
Oxidation state 0. And it has become a calcium +2.
Bam.
When it's in the compound. So in this case, the pure element became a cation.
Correct.
By losing electrons.
Now, when we do these half reactions, we track and throw the electrons in the right spot, and we're good.
Yep.
So we'll start out with the first one.
So we can put the electrons on either side of the arrow, but where do they go?
Oh, so honestly, this is almost what makes sense. Does Mg +2 + 2 electrons equal Mg0? Does that even make sense? Mg +2, 2 extra protons. I need 2 extra electrons to become 0. That does make sense. If you were to do it the other way, if you were to say Mg +2 goes to Mg0 + 2 electrons.
You created 2 electrons out of somewhere.
And where'd you get then
where'd they come from?
Yeah, that doesn't work.
So click again and you'll see that that's right. That is the correct half reaction.
That's what you're writing. We're trying to talk you through figuring out where to put those electrons.
This is technically a reduction half reaction because reduction is gaining electrons.
Correct.
So let's check out the oxidation half.
Well, again, we got that initial Ca0 and Ca +2 that we already figured out.
Where do the electrons
Where do the electrons go? I'm not really sure, but okay, so C0.
If I added 2 electrons to elemental calcium,
it would be a -2.
It would be a -2 charge.
So that doesn't work.
That's not going to work.
2.
So let's get rid of that 2 electrons there. And there is our oxidation is losing electrons. That's our oxidation half reaction.
There you go, because losing goes on the product side. Mm-hmm. And notice, if you write these things properly, electrons are on one side on one and on the other side on the other.
Yeah, the same amount of electrons.
That's a whole fact.
Absolutely. So let's see what we got to do. Overall reactions that are half reactions show both the half. They actually combine the two.
That's that picture from vocab. Remember, it showed the 2 and then it added them all up.
Yeah, they do look a little messy because there's ion charges and all that stuff, but that are really not.
Yeah. Then the reduction shows just the elements that's being reduced. Both forms of the metal are shown, one with a 0 and one is a cation or anion, right? And then
metals only make cations, really.
There you go. Thank you. And the cation, and then the number of electrons gained on the reactant side. So the reduction half reaction has electrons on the reactant side.
Mm-hmm.
Reduction, reactant. Ooh, that might help.
Somebody will help somebody help. Just the element that is being oxidized shows up in the oxidation half reaction, and both the forms of the metal, so the ion and the atom, and the reactant is product with a number of electrons losses on the product side. So, yeah.
Now that we did the notes on it, I think we actually have to do it so we figure it out.
Mm-hmm. But we want to let you one more thing, because in our practice, we really wanted to enforce reducing and oxidizing agents. It was on the Regents exam a couple years ago, and it really bit us in the butt because we were like, it's not going to be on there this year, and then it was. So every oxidation and reduction reaction has to accompany with an oxidation and reduction agent.
Kind of a fact, because there's always both,
And so oxidizing agents are the elements that got reduced themselves.
Sure.
Because they allow for the transfer of electrons in that case.
Right. They make the oxidation possible to providing themselves being reduced. And the exact opposite is true for the reducing agent. It's the element that's being oxidized. Again, it's responsible for losing the electrons gained by the atoms that are being reduced.
So we call it the agent.
Right.
It's tough, but it's not.
It's kind of like, I think a lot of it, like, a player having a sports agent, one's actually doing stuff and then.
Let me do the first one?
Oh, yeah. Okay.
First thing you always do
And we didn't really do this in the notes, but this is how we actually do it. We go ahead and start putting in the oxidation numbers. So start with the zeros on the lone elements. And then I usually start with the negative, but in this case, you can do the positives because ZN only has one choice and Mg only has one choice. Cl only has one negative choice. So right there is all our oxidation numbers. So now we can pull it out and say Mg0 goes to Mg plus 2. Whoa, how many electrons do you think that happened if I go from 0 to 2? 2. And now the other piece we miss with the oxidation reducing agent, ready? You can never pick him from the product side. Okay, it's always on the reactant side. So he's jumping ahead to Zn and then do the agents last.
Because I always do my agents last. I look and say, okay, if it was oxidized, that means it was the reducing agent.
Right.
And if it was reduced, that means it was the oxidizing agent. So I look now,
right.
I say magnesium it lost electrons. And oxidation is losing electrons. So that means it's the reducing agent.
Correct.
So I will say that Mg0 is the reducing agent.
Correct.
And now I look at the other reaction, the other half reaction. Zinc picked up 2 electrons. Reduction is gaining, reduction is gaining electrons. So that was reduced, which makes zinc plus 2 the oxidizing agent.
Correct. Don't be tripped up if the oxidation reagent starts switching on you to make you think.
Mm-hmm.
We don't want you to get into a pattern.
Your turn, Milks.
The pattern I want you to get into is writing those charges first.
And working out the rest. So
okay.
He's going to hit up his pure elements first with oxidation state 0.
Bam 0.
And then he's going to figure out what the oxidation state
first.
Chlorine is. 99% of the time it is. When chlorine's involved in a oxidation reduction, when it's in a binary compound like this with 2 elements, it's always going to be -1.
Yeah, especially when it's the second one. So Hg0, I got that here, goes to Hg with a +1.
Mm-hmm.
And 0 to +1 is only 1 electron.
1 electron. And then he's got to look at the other guy.
Ag +1 goes to Hg0.
Ag0. Too many G's in this one.
Oh, yeah. And then 1 to 0, so 1 electron.
Mm-hmm.
Okay, oxidation is Hg0 is being oxidized, so it must be the reducing agent.
Absolutely.
And then if Ag +1 is being reduced, it must be the oxidizing agent.
Exactly.
Remember, we only pick those agents off of the reactant side.
Yes. No product will ever be an agent.
No.
Because these are one direction reactions. They are not equilibriums.
Mm-hmm.
So not going to work like that. So he's going to pick up the pen and pick up the pure elements. Perfect.
Can I keep the polyatomics together?
Keep the polyatomics together.
That really makes life a lot easier.
Absolutely.
Now, I got there's 1 -1, so that's a +1.
Yep.
But there's 2 -1,
so that's
he's
a
+2. Because of that, 2.
Mm-hmm.
Okay. So
and this is great because what we're going to do is we're going to track oxidation in copper.
Cu0 to
Cu plus 2. Mm-hmm.
And I'm always going to write the Cu plus 2 first. I like to do the electrons last here. So 2 electrons, 0 to 2.
Mm-hmm. Now the silver ion +1 became silver element 0. So it must have picked up 1 electron.
Plus 1 electron.
Now stop, Mr. Milks. There's a problem.
And that don't equal.
We're saying that copper loses 2 electrons, but silver only picks up 1. That's impossible. We have to balance these equations too. So the easy way to do it is this. You double the amount of silver. So technically we'd have to squeeze a 2 moles in front of the AgNO3 as well.
Yep. Oh, way up here?
Yep. We'd have to squeeze a 2 in there to make sure that it balances properly. He's just rewriting it over to show that he's doubled the reaction. And we just got to identify our agents, and there you go.
And then, okay, so if this is the oxidation and he's being oxidized, he must be the reducing agent.
Mm-hmm.
And if this is the reduction, he must be the oxidizing agent.
There it is. So, redox half reactions. There's a reason why there's a lot of practice in it, because we don't believe that you really have it 100% after that 9-minute video.
Yeah, because we got to do it a lot.
You just have the basics of understanding.
Here's our saying, right? We're not going to practice until we get it right. We're going to practice until
we can't get it wrong. That's all, folks. I hope I don't get sued by Porky Pig and Warner Brothers.